In the last presentation, we arrived at the definition of standard error, which is synonymous with random sampling error, the standard deviation divided by the square root of n. Let's return now to our student pollsters and find out how the knowledge of the standard error can help them determine or help them estimate where the population mean lies. Just to reiterate, well, let's assume that the pollsters took a random sample of n1 equal to 100 from population A. Remember, that was a population with a standard deviation of about 25. It was 24.8. And they obtain a sample mean of 59. Therefore, the standard error associated with that sample mean, the amount of random noise in that sample mean, is equal to 24.8 divided by the square root of 100, or about 2.5. So now we have a sample mean of 59 and a standard error of 2.5. How does this number, 2.5, help the pollsters figure out the true value of mu? Let's apply the standard error. Let's begin to apply it, and I've abbreviated it SE. And also, I should say, we are omniscient. We know about the population. We know what the population mean is. We know what the population standard deviation is. And we're watching the student pollsters try to find out how far away their estimate is from the true population mean. Here's what we know. Given a population mean equal to 58 and an SE equal to 2.5, here are some things that a standard established statistical rule called the central limit theorem allows us to know. 68% of all random samples of size 100 will yield sample means between 58 plus or minus one standard error, plus or minus in this case 2.5, or between 55.5 and 60.5. So 68% of random samples will fall in that interval. 95% of all such samples will yield sample means between 58 plus or minus 2 times the standard error, or in this case between 53 and 63. We are dealing with random processes here, so there's a remote but real chance that random processes will produce bona fide flukes. We might get a mean that is below 53 or above 63. In fact, 2.5% chance below 53 and a 2.5% chance above 63. Now, let's illustrate where these percentages come from and illustrate the central limit theorem. And in doing so, we'll produce what's called the sampling distribution of population A given sample sizes of 100. Now recall, in the earlier presentation, we took 10 samples of size 100 from the student population A, and we looked at how those were distributed. Now, imagine taking a very, very large number of samples from that population. In fact, imagine taking 100,000 samples of size 100 and recording the mean of each of those samples. What would this distribution of 100,000 sample means look like? It would look like this. Each of those 100,000 sample means is recorded on this bar chart. And this has a familiar shape, doesn't it? The first thing to notice about this is if you take a very large number, in fact, the theorem says an infinite number of random samples of size 100 from that population, it will have a normal shape. This is called the normal distribution. The normal distribution, as we'll see in a bit, has known properties. In fact, one of the things already stated is that here's the population mean. If we go out here to 60.5, and then we come down here, say to 55.5, that interval contains 68% of all possible sample means. If we go out to 63 on the high end, or down here to 53 on the low end, that interval contains 95% of all possible sample means. So that's the first thing to notice. The other thing about this is if we added up all these sample means and took the average of them, added them all up and divided by 100,000, we would arrive at, the result would be the true population mean of 58. So let's review those facts and talk about the central limit theorem. The central limit theorem states, if we were to take an infinite number of samples of size n from a population of n members, the means of these samples would be normally distributed. Also, the distribution of sample means would have a mean equal to the true population mean and have random sampling error, or standard error, equal to the standard deviation over the square root of n. Furthermore, and therefore, most random samples of n equal 100 drawn from a population where mu is 58 and the standard deviation is 24.8 will yield means that are equal to 58 plus or minus 2.5, as we've seen, between 55.5 and 60.5. I just note here that the student pollsters mean of 59 falls in this high probability interval. You know, when they reached into that population and took that sample, there was a 68% chance they would get a mean in that interval, and indeed they did. Now let's talk then about the shape of the sampling distribution. We know about the central limit theorem. The central limit theorem says the distribution will be normally distributed. What is the normal distribution? The normal distribution allows us to make precise inferences about the percentage of sample means that will fall within any given number of standard errors of the true population mean. But to get there, we have to convert units of measure, in this case means on a democratic feeling thermometer, say 58 and 59 and so on and so forth. To get to the inferential power of the normal distribution, we need to standardize each of those observations, each of those sample means, and transform them into units of standard errors. When you do it, it looks like this. So for example, any sample mean that falls right on the population mean of 58 has a z-score of 0. The student pollsters are right there. They are 1 unit above the true population mean. True population mean is 58, they're at 59, so they're at 1 unit above. If you convert 1 unit of measure into standard errors, they're at almost precisely 0.4 of a standard error above. So their z-score, the z-score of their random sample is plus 0.4. We'll talk about this a little bit more, then come back to the distribution of z-scores. The normal distribution is a distribution used to describe interval level variables. To use the normal distribution, we first need to standardize each of the 100,000 sample means by standardization. Standardization occurs when the numbers in a distribution are converted into standard units of deviation from the mean of the distribution. And of course, the unit of deviation we're using is the standard error. To standardize the distribution of sample means, we would subtract the population mean from the sample mean and then divide by the standard error. So sample means that are below the population mean have negative z-scores. Sample means that are above the population mean have positive z-scores. And any sample mean that falls right on the population mean has a z-score equal to 0. Here's the formula. We standardize the distribution and obtain a z-score for each mean, each sample mean, by subtracting the population mean from it, so it's x bar minus mu, divided by the standard error. So back to our student pollsters, their z-score for their random sample is 59, which is their observed sample mean, minus 58, which is the population mean, divided by 2.48, which is approximately equal to 0.4. So the pollsters mean lies 0.40 standard errors above the population mean. And again, here's that distribution of z-scores. We happen to know, thanks to statisticians, that if we go from -1, a z-score of -1, to a z-score of +1, again, that's the interval that contains 68% of all possible sample means. If we go down to almost -2, in fact, the iconic true value is -1.96, often rounded to 2, or -2, all the way up to plus 1.96, or 2, that interval contains 95% of all possible sample means. So we can calculate areas under the curve by knowing these elements of the central limit theorem. And that's where the inferential power comes from. It comes from these standardized conversions of sample means into z-scores. Once a distribution is standardized, we can use the normal curve to determine the probability of observing any given sample mean by chance. There's a chance probability of reaching into that sampling distribution and pulling out a mean of, say, 62, or pulling out a mean of, say, 68. That would be very remote. Or pulling out a mean of 58.2 or 57.1. Those would be highly probable. So now we have a device, we have a vehicle, a tool for determining the probability of observing a certain event, or of observing a certain sample mean. What is a probability? A probability is defined as the likelihood of the occurrence of an event or set of events. And here are the probabilities associated with the normal curve. And you may have seen these before, and I've mentioned these particular percentages several times now. There we go. Between z-scores of -1 and +1, 68% of the distribution lies in there. And then, of course, since the distribution is perfectly symmetrical above and below z of 0, we know, for example, that 34% are going to fall in the bandwidth between z-score of 0 and +1. And then 95% between -1.96 or -2 by conventional rounding, and plus 1.96 will contain 95%. And then, of course, out here in the tails, beyond those two extreme values, you find 2.5% out here above 1.96 and 2.5% down here below -1.96. So let me just reiterate those before moving on to the next presentation. 68% of all possible sample means will fall in the interval between one standard error below the population mean, a z of -1, and one standard error above the population mean, a z of +1. And 95% will fall between a z of -1.96 at the low end and a z of +1.96 at the high end. 5% of the time we obtain sample means that are wide of the mark, and this is just by chance. There's nothing, no systematic processes doing this. Chance will produce these flukes. 2.5% of the region below z of -1.96, and 2.5% in the region, I should say above, a z of equal to +1.96.